Hi there. In this video we're going to look at how we differentiate parametric equations to find the gradient at a given point. So you might recall that parametric equations are given where y is some function of a parameter, in this case t, and x is also some function of a parameter, in this case t. So I've drawn a quick sketch of what one of these curves might look like. Obviously this works generally, but just sort of help visualize what's going on. So it might be sensible to ask, at a specific point on our curve, what is the gradient of the tangent to that point? Okay, and as we know, gradient is given by dy dx. Now this causes a little bit of a problem here because we don't have y as a function of x, we have y as some function of t. Now, one way that a lot of students go about attacking one of these problems is to rearrange the second equation to make t the subject and then substitute that into their equation for y to come up with their Cartesian equation and then differentiate that as they normally would at that point. However, sometimes it's not always possible to make t the subject of x, and very often that's actually much more complicated than using the little trick we'll show you, which is applying the chain rule. So as you'll recall, the chain rule is dy du times by du dx is equal to dy dx. And we're going to use this fact to help us figure out what we need to do over here. So from this first equation, if we differentiate this, so from equation 1, this gives us, if we differentiate this, we can find dy dt, and similarly from equation 2 we can find dx dt, just by differentiating how we normally would. Now if we want to work out what dy dx is, then we need to think, how can we combine these three things in the chain rule to give us something involving dy dx, dy dt and dx dt. Now the most obvious way we can rearrange this is to have dy dt is at the front, and then that is equal to dy dx times by dx dt. Now, one last problem, again, we're after dy dx, and dy dx isn't the subject of this, but that's not too difficult to fix because we can just rearrange this formula. So we get dy dx is equal to dy dt divided by dx dt. And that is how we differentiate or find the gradient of a curve given it in parametric form. Okay, so in our first example of this, we're given a parametric equation, x is t squared minus 2 and y is t cubed minus t, for values of t strictly greater than 1 and less than or equal to 2. And in this case we're actually given a sketch of what the curve looks like. And for the first part we're asked to find dy dx in terms of our parameter t. So you remember that before that dy dx is equal to dy dt over dx dt. So our strategy is going to be to find dy dt, to find dx dt, and then substitute them into this formula. So let's look at equation 1. So from equation 1 we have dy dt is equal to, well, this one's quite easy to differentiate, it's just a polynomial. So bring the 3 to the front, so we get 3t squared, and then minus, well, the t just turns into a 1. Similarly, looking at equation 2, we're going to find dx dt. And again, very simple to differentiate. We get 2t minus 0 in this case, which we don't need to write. So then our final step is to substitute these into this formula. So we get dy dx is equal to 3t squared minus 1 over 2t. And then that's our final answer. We can't simplify that any further because we've got an addition on the top. And this would factorise because it's the difference of two squares, but not to something that's going to cancel with our 2t on the bottom. And in this case, I think you're not gaining anything by splitting it into two fractions and simplifying that way. So I think that's probably concise enough for what we need it for. Okay, so moving on to part B now. Find the gradient of the curve where x is equal to 1. So we've just differentiated to find dy dx, and we derived this formula, and now we need to find the gradient of the curve when x is equal to 1, which is going to be about there. So we're expecting our gradient to be positive, and it looks like it's going to be quite steep as well. Now, we're given a value of x, however, our gradient function dy dx is given in terms of t. So we need to use what we know about parametric equations to find the values of t given our value of x that correspond to this. So again, we'll look at equation 2. So we're going to substitute. So sub x equals 1 into equation 2. And that's going to give us 1 is equal to t squared, take away 2. Now this is a fairly easy equation to solve. We're going to add 2 to both sides. 3 is equal to t squared. Then t is equal to plus or minus the square root of 3. Now we just need to have a quick look to make sure that our value of t, both values of t are valid. And it turns out that actually, because t has to be bigger than negative 1, t can't be equal to negative root 3. So actually t is just equal to the positive value of root 3. So now what we can do is, because we know what t value we're after, we can then substitute our value of t to find our gradient function. So sub t equals root 3 into dy dx. So let's have a go at this then. Dy dx is equal to 3 root 3 squared minus 1 divided by 2 root 3. And now root 3 squared is just 3, so this is equal to 3 times 3 is 9, take away 1 is 8 over 2 root 3, which simplifies down to 4 over root 3. If we were to rationalise the denominator of that, we'd get 4 root 3 over 3. Again, in this case, because it's not asked us to write it in a given form, we don't need to. But that is something we could do if we wanted to. Okay, on to part C. So we're now asked to find the coordinates of the points where dy dx is equal to 0. So remember, a 0 gradient means that our tangent is horizontal. So we're after these 2 points here, where the tangent to the curve is horizontal. So our general strategy is going to be to set dy dx equal to 0 to give us a value of t, or some values of t. And then once we've got those values of t, the question does ask for the coordinates, so we need to substitute that in for x and y to get our corresponding x and y coordinates. So first things first, let's set dy dx equal to 0. So we get 0 is equal to 3t squared minus 1 over 2t. Now if we want a fraction to be equal to 0, we actually need the numerator to be equal to 0. We just need to be a little bit careful. If we get t is equal to 0 as one of our solutions, the dy dx isn't actually valid at that because we get a division by 0. But we'll cross that bridge when we come to it. It's just worth thinking that we should be wary of whenever t is equal to 0 here. So if we want the numerator to be equal to 0, we get 0 is equal to 3t squared take away 1. Not too tricky to solve. We'll add the 1 to both sides and then divide by 3. So we get t squared is equal to 1 over 3 And then if we square root, that gives me t is equal to the square root of 1 is just 1, and the square root of 3 is root 3. And that is plus or minus as well. So it's just an extra thing we need to consider, that there's 2 possible values there. Okay, so now our next step is to sub in plus or minus 1 over root 3 to find x and y. So let's start with x first of all. So we get x is equal to 1 over root 3 squared, take away 2. Now 1 over root 3 squared, that's just going to give me a third. So we get x is equal to 1 over 3 minus 2, which is equal to negative 5 over 3. So our value of x is negative 5 over 3. Now, we've only substituted in our positive version there, and we also need to substitute in our negative version. So let's just consider what happens if we make this negative here. Well, negative 1 over root 3 squared, and if we square a negative, it becomes positive. So this still turns into a third, and this still stays as negative 5 over 3. So for both of our values, plus or minus 1 over root 3, we're going to get the same x coordinate, which, looking at our curve, kind of makes sense. It certainly appears as though those 2 points are on the same vertical line, which means that they've both got the same x coordinate. And so this sort of confirms what we might suspect from our graph. So now let's have a look at y. So y is equal to t cubed minus t, which is going to be 1 over root 3 cubed, take away 1 over root 3. Well, 1 over root 3 cubed, well, 1 over root 3 squared was a third, so 1 over root 3 cubed, we times a third by 1 over root 3, that's going to give us 1 over 3 root 3, and then take away the 1 over root 3, and that's our next step. So now we have to subtract these 2 fractions, and to do that we need to give them a common denominator. In this case, it makes sense to put them both over 3 root 3, so let's do that now. So that gives me 1 over 3 root 3 minus 3 over 3 root 3, which then gives us negative 2 over 3 root 3. So our first coordinate is negative 5 over root 3, negative 2 over 3 root 3. And that corresponds to, well, if our y coordinate is negative, that's going to correspond to this point. So that gives me negative 5 over 3, negative 2 over 3 root 3. So now we need to work out what our other coordinate is, and to do that we're going to find out, we're going to look at the negative value in our y coordinate here. So if this is negative, well, a negative value cubed stays as a negative. And if this here is negative, if we're taking away something that's negative, that turns into a positive. And now what we can do is we can pull a factor of negative 1 out here. So that gives us negative 1 multiplied by this, which then means we get negative 1 times by this. Now if we take negative 2 over 3 root 3 and times it by negative 1, that's going to give us our second solution as positive 2 over 3 root 3. So our second solution here is minus 5 over 3, and this time positive 2 over 3 root 3. Okay, so there are 2 coordinates where dy dx is equal to 0. Okay, on to part D. So this time we're asked to find the coordinate of the point where the curve attains its minimum x value. So x, let's have a look at our curve, is increasing in that direction, so it attains its minimum at this coordinate here. Okay, that's the smallest the x value of the curve gets. So there's a couple of ways we could look at doing this. The first way is to take dy dx and flip it on its head, quite literally. And the second way is to differentiate x with respect to t and then find the minimum value there. I'm going to have a look at the first method, looking at dy dx, and then we'll sort of see that actually those two methods are quite similar. So if we want the minimum x value, well, dy dx isn't much use to us here, because you'll notice that at this point the tangent is going to be vertical, which means it's not going to have a well-defined gradient dy dx. What we can use, however, is we can use the fact that dx dy is equal to the reciprocal of this. And now, because we're looking at dx dy, suddenly this value here, the gradient in terms of dx dy, is well defined at this point, and it's equal to 0. So now we're going to use the fact that dx dy is equal to 0. So again, if we've got a fraction equal to 0, we only need the top to be equal to 0. So that gives me that 0 is equal to 2t, which gives me that t is equal to 0. Now in part C, we noticed that in dy dx, t couldn't be equal to 0, because then dy dx wouldn't be valid. And this is why, because at this point dy dx isn't valid, because it would actually tend to infinity as t gets closer to 0. So what we're going to then do is, again, ask for the coordinates, so we need to substitute t equals 0 into x and y. So let's do that. So x, well, if t is equal to 0, then x is equal to 0 squared take away 2, which is just negative 2. And if t is equal to 0, y is equal to 0 cubed take away 0, which is equal to 0. So our coordinate is negative 2, 0, which means this point here is negative 2, 0. Okay, so as I said, the other way we could do this is to find dx dt and then make that equal to 0. If we're finding the minimum value of x, as you'll have seen before, if we differentiate it and then find where it's equal to 0, that gives us our minimum value of x. Now, this is exactly what we've done, really. Recall how we worked out what dy dx was. Well, dy dx was equal to dy dt over dx dt. This means the reciprocal is dx dt by dy dt. And then if we need the numerator of this fraction to be equal to 0, then all we've done is we've set dx dt equal to 0, which gives us our minimum value using our what I refer to as a second method, but it's all part of the same method. And then that's it. That's parametric equations differentiation.